The webinar will begin in 1 minute. Good morning, everyone. I'm Christy, and I'm one of your moderators today. I know your schedules are very busy, so thank you so much for taking the time to spend it with us. Before we dive in, let's quickly run through just a few housekeeping items. Today's session will be for 1 hour and will feature multiple speakers, Mr. Michael Goff and Mr. Jerry Lanting. We've also have live polling questions that are going to pop up on your screen, so please make sure you interact. If you encounter any technical issues along the way, just drop a message in the chat box and we'll swoop in as quickly as possible to help. Hold on to your questions until the end. We have a dedicated Q&A session for that. And if you look over onto your screen, there's a tab that says Q&A where you can type your questions. We won't answer those questions until the end though, on a dedicated time, but we'll get to each question as time allows. Lastly, when we wrap up, we do have a survey that we would like for you to fill out. It helps us improve our webinar techniques and lets us know what you want to hear. So with all of that out of the way, I'm going to turn it over to Mr. Michael Goff. Mr. Michael Goff is Menardi's national manager, and he has over 15 years of industrial experience. So without further ado, Michael, take it away.
Great, thanks, Christy. Good morning, everybody. And first of all, I'd like to echo Christy's sentiments. I really appreciate you guys taking some time out of your day. We know you're busy. We hope you're able to pull some value out of today's discussion. Our goal is to give you some of our ideas surrounding maintenance, design, troubleshooting, and strategies that you're able to take back and use every day to help you, A, understand your systems better, B, the role of preventive or predictive maintenance, how those things differ, different troubleshooting strategies and documents to help you take watch of that, and just overall to make things more predictable for you. We'll spend some time going over this type of content through the slide presentation and some pictures, and then we'll round this out with some of Jerry's case studies that highlight some real-world applications of some of the things that we're going to be talking about. So with that, I'm going to turn it over to Mr. Jerry. Thank you.
Hey, thanks, Michael. Like Michael said, my name is Jerry Lanting. I'm one of the senior regional sales managers with Menardi. And this webinar is called Beyond the Basics, but I don't think we can really talk about things that are beyond the basics without at least touching base on some of the things, some of the basic parts of the baghouse and filters and things like that. So I just want to run through these. Just take a few minutes and run through some of these. And some of the things we're going to talk about is the difference between positive and negative pressure, types of baghouse systems, common issues affecting baghouse efficiencies. The first and the least common when it comes to the fan is your positive pressure baghouse. This is a baghouse where your fan is on the clean side or on the dirty side of the baghouse. So it's going to be somewhere between your pickup points and the baghouse, somewhere in the ductwork, and it's going to pull the air from the pickup points and then force it through the bags, through the filters, and out the stack. The next one is the negative pressure baghouse. This is the most common. This is what you see. This is what I've seen out in the field probably 95% of the time. Actually, probably more than that. But it's where the fan is on the clean side of the baghouse. It is drawing air, it is pulling air all the way from the pickup points to the baghouse, through the filters, out the inlet, out the outlet, and then pushes it through the stack. We do have, Christy mentioned earlier that we're going to have a few polling questions throughout this webinar. And the first one is, what type of baghouse or baghouses do you have at your plant? So if y'all can answer that, that just kind of helps us get some more information from you guys and how we can better serve you. But as y'all are answering that, let's talk about the three types of baghouses. Each of those baghouses, that they are named after the way that they clean. So the first one is a shaker baghouse, not very common. It's an older style as far as large shaker baghouse. You do still see some newer shaker baghouses, but it's really in the oil and gas industries or little bin vents. But they're 15 to 48 filters per each one, just small. But as far as the large collectors, shaker baghouses, that's old technology, and you just don't see much of them out there anymore. But just a little bit about these: you'll have the inlet gas come in either in the hopper. Your tube sheet is low. The bags are attached to the tube sheet at the bottom of, just above the hopper. The bags are hanging from the top. And the inside of the bag is your dirty side, and the outside of the bag is your clean side. And again, you isolate the compartments, and it shake. The bags relax. They shake. Dirt falls down to the hopper, gets evacuated out of the hopper, then it comes back online. The next one is a reverse air baghouse. Same concept as far as tube sheets low, right? And then the dirt comes inside, clean side, or the dirty side is the inside, the clean side is the outside. The exact same structure as the shaker baghouse, with the exception that it cleans differently. Still isolates the compartment, dampers close, bags relax for a moment. The reverse air fan comes on, the bags suck in, and then relax again. The product falls down to the hopper, it comes back online, and then you're good to go. And then the next one is the pulse jet. Now, the reverse air and the shaker, again, still old technology. You don't see those anymore. Nobody's going to go out and buy and build a new reverse air baghouse. They're all going to be pulse jets. And the reason being is the shaker and the reverse air all have to go offline to clean. The pulse jet baghouse is the baghouse where you don't have to do that. It's continuous cleaning. It cleans while it's running. So it's kind of looks the same sometimes. You have the dirty air still coming in at the hopper, comes up, but the tube sheet's up high and the bags hang low, and the outside of the bag is your dirty side and the inside is the clean. So it's off, and these are cleaned with compressed air, usually blow tubes above each of the holes of the filters, pulses air. There are some different styles there, like a plenum pulse, where it's one big push of air through there, but the bags themselves are being cleaned with compressed air. So those are the three different types. Again, they're all named by how they're clean. Common issues affecting efficiency. There's so many different things that cause your baghouse not to run or work properly, or prematurely failing on bags. You see this picture right here where you see some broken wires on a cage. A broken wire on a cage is not your friend. As your bags are being cleaned, as it pulses, that bag expands, that filter expands and contracts, right? And what is it going to do? It's going to rub on that broken wire. It's going to cause a hole. You get a hole in your bag. You start introducing product onto the clean side of your tube sheet, and then it pushes product on the inside of other bags surrounding that. And before you know it, you have an entire compartment or bag house with compromised bags. So these are things to look for. as motor failure. The other one is that center picture is going to. There's a lot going on with this. You have either some abrasion going on, and you're busting out the bottom. So you've got, there's a lot of different things you could do about abrasions, or it could be heat related. You see the bags that the media is kind of folded up. That's usually a sign of heat. So are you using the correct bag in your bag house? These are all things that we can help you with as we're out in the field. Also, the other slide is cracks in your ductwork. If you live in an area, or if your plant is in an area where you have a high moisture content, um, those things are not your friend. Your fan is going to pull that moisture in, and we've got some case studies where I'm going to talk a little bit about that in a little while. Real life things that we were able to see. Door seal. Again, if your doors are not sealed on your bag houses, and especially if you live in an area where there's a lot of humidity, a lot of moisture is present, you're going to pull that in your bag house, and it's going to cause premature bag failures. Holes again. There's another picture with a hole and a ductwork on an inlet coming in. That's sucking moisture right in. Your equipment, magnet helix gauge or your photo helix gauges, or any kind of your sensors that are in your bag houses, knowing that those things work and working properly is key. I tell people all the time, your bag house is only going to run as good as your equipment is, and understanding what you have and what your equipment is supposed to do will give you a better chance, or a better fighting chance on your bags. Another thing I preach all the time when it comes to some of your older plants out there. When your plant was built 40 years ago, that plant was designed to do X amount of product per day, per hour, however you want to look at it. Well, as you know, most of y'all know, that number is now 3, 4, 5, 6 times that the expectation, but with the same equipment that you had. They didn't upgrade your equipment. You're stuck with the equipment that you have. So understanding all the parts of your equipment, all the working things of your equipment, to be able to give you the max output and performance out of your bag house is very, very important. Preventive maintenance practices, guys. There's a lot of charts and documentation that you can do. Regular inspections and cleaning, importance of proper documentation. Okay, so these are some of the checklists that we have, that we kind of said that these are our recommendations, right? I tell people all the time, I can give you these recommendations, I can share these things with you, but you need to take what we recommend and apply that to what your plant needs, because everybody's different. Everybody needs to look at different things, but these are just kind of a general rules. So you got daily inspections, walking through the baghouse area, check for normal and abnormal visual and audible sounds. That's a crucial thing, right? Knowing and understanding what a failed diaphragm sounds like. If you understand, if you know what that sounds like as you're walking through the plant, you may be headed to the opposite side, but you walk by a baghouse and you hear that sound, you call someone on the radio, say, hey, look, this baghouse, so and so baghouse, you've got a failed diaphragm on your pulsing system. It needs to be changed out. Somebody can get there, change that thing out, making your baghouse run the way that it needs to run. Check, looking at your differential pressure, understanding what that looks like. If differential pressure is climbing and that's abnormal, that means you probably got some failed bags in there somewhere that are plugged up and you're not getting the flow that you need. Checking your cleaning cycle, making sure, there's just a lot of different things. Weekly inspections, check the seating conditions of the bags. I said earlier that this is just our recommendations of a checklist, right? I know several plants where you're not going to get in a baghouse. You're not going to be able to open the door to a baghouse every week to make sure that those bags are seating properly in that tube sheet. They're just, you can't do it. There's a brick plant that I go to quite often. I was just there last week. They can get in their bag house when they shut down, and that's like once every 2 or 3 years. So they just can't do it. So again, these are just suggestions. Spot check bags for leaking holes, moving parts, shake your bag house, check fans for corrosion, check all your hoses and clamps, the poppet valves, make sure that those are working. And then there's a suggested monthly inspections. Blow out clear magnet helix gauge lines, verify the working order, the temperature indicated equipment, make sure that your temperatures, that it's indicating the correct temperatures. That's very important because, as a lot of y'all know, you put in certain medias in your bag house based off of the conditions of your bag house, and temperature is a big factor. Check the bag cleaning sequence to make sure that those are correctly. If you are not sure how your bags or how your cleaning sequence is supposed to be, let us know. We would be more than happy to come out on site and make sure that you are cleaning the properly. And then you got a quarterly inspections, thoroughly inspect all bags, do a leak check if you can, calibrate the opacity monitors. There's a list goes on and on. Check the rotary airlocks, the screw conveyors, and we're going to talk a little bit about some case studies when it comes to things like that. Why it's important to check those quite often. And then here's some yearly inspections. These kind of gets really deep into the woods, like check the bolts, make sure that those are good, check the ducts for dust buildup. And if you don't want to climb through your duct work to make sure that there's buildup, I can send Michael Goff, my manager, out there he'll climb through your ducts and clean them for you. Just joking. Just check everything for proper wear. Your hoppers, make sure those are good. Your sonic horns, make sure that those are working correctly. If you are curious what sonic horns are, please reach out to us. We can kind of help you explain what sonic horns are and if that could be a good fit for your plant. So here's the next polling question. How often do you document maintenance activities? So there are several things that we use, that we have, forms, documentation forms to be able to help understand what you have, and it helps you understand what's been problematic. We have a bag house inspection report that we do when we go on site. We have a failed bag location chart. That's very important. Knowing if you constantly are having bags fail in a compartment, document which ones they are. And that could tell us and tell yourself that you have a problem in this area. If it's random, then it's random. Then we find out what your other mode of failure is. Then we have what we call our FITS form. These are forms that we have to be able to give to you, or that we use on site to be able to measure bags, cages, pleated filters, whatever your equipment is, so we can make sure that we get you the best possible filter that fits correctly in your plant. We don't just take your word for what it is. A lot of, we want to get on site with measure a tube sheet, mica tube sheet hole, make sure that snap band is fitting in there correctly. Not necessarily just it pops in really easy, but then it pops in really easy and it seals, so you don't have any bypass and have catastrophic failures within your bag house. So all the checks in the world don't matter if you don't keep track of them. So with that being said, I'm going to turn this back over to Michael, and he's going to talk about some more stuff.
Thanks, Jerry. On the heels of all these basic maintenance practices that we've been talking about so far this morning, I'll be talking about some more advanced maintenance topics. Just quickly covering predictive maintenance, how that might differ from preventative maintenance, equipment upgrades, filter construction, and how empowering your personnel through encouraging ownership and accountability of the equipment may help you with reliability. On this first slide, we're looking at tension and how that plays a role both from a preventative standpoint and predictive. This is primarily involving reverse air and shaker collectors. So of note is we expect that tension should change over time. You guys that have reverse air and shaker bag houses out there, you know everything there is to know about initial tension requirements when you're installing these bags. Those of you that have hardware, what that spring load design is, cleaning systems, et cetera, et cetera. But the tension that changes and how that changes will help you determine or help you predict what that life cycle might be according to those changes. So when you're looking at the picture on the right, this is a good visual check, assuming the rings are all designed to be in the same place. Crack open the door and see if that ring placement has changed. Fifth bag back from the wall, the rings are 2 inches lower than everybody else. Let's go up top and see what the spring looks like. So these things are going to move. They're designed to move. The predictive side of this, just, hey, if we do everything that we can from an initial loading standpoint and preventive maintenance, how are those bags that are a little bit less tensioned, how is that going to show up in overall bag life? Differential pressure. Everybody's got differential pressure, whether it's compartment by compartment or flange to flange on an entire collector. But this is the heartbeat of your system. This tells us how healthy we are. You have to be able to clean if you're going to have a multi-cycle filter system. But more importantly, you have to be able to trust that your instrumentation is giving you the right information. So this next slide is going to give you an example of how you might manually calibrate to ensure that what information you're being given is accurate. So this would walk you through the process of manually verifying that the information is accurate. It includes cleaning out the airlines and just kind of double check. From a predictive maintenance standpoint, again, cleaning on demand versus cleaning on time. I'm not going to go into this a lot because this is in some of Jerry's case studies at the end of this or on the tail end of this presentation. But I will just mention to pay careful attention to those set points. Where's the high end, the low end, and what is that gap between? Cleaning on demand versus on time is heavily involved in predictive maintenance and that total cost of ownership. So those are the reasons that drive somebody to move from a continuous cleaning versus a clean on demand. We've got another poll question coming your way. How often do maintenance and operations routinely perform routine maintenance? So we appreciate your feedback on those. All right, this next section, we start talking about equipment changes or filter changes that you might not have considered that may help with your reliability. We'll also talk about those unintended consequences sometimes of upgrades and how empowering your maintenance personnel might help you with reliability as well. And I'm gonna steal a phrase here from Department of Homeland Security: if you see something, say something. So this next slide is all about equipment upgrades. So in some sense, filtration equipment can feel like buying a computer. They used to say that as soon as you bought a computer, it's already out of date. And what you're looking at here was something that was probably cutting edge technology of its time. This is a flat flange seal, and this is just a picture just to kind of illustrate there could be a better way. There could be a better way to seal this, both from a emission standpoint and a change out, labor standpoint. These next few slides, we'll talk about filter changes. This first one is a bottom load filter. This dominates the air pollution control industry. Everybody's got a bottom load filter out there somewhere. That's a raw edge bag that you attach to a cage, and then attach that combo to a bottom hub with use of a hose clamp, some type of a clamping system. And you see the picture there to the left. If the bag is either not sized properly, or it's a heavy bag material, sometimes you can get some pinch points in there that can cause some emission issues. So a potential filter upgrade to help combat that is what we call a soft seal, where that top section that is meant to tuck into the cage is made from a little bit different material to help you create a better seal when you attach it to the hub. The next one, again, kind of a similar story. This is a compression fit that uses a clamping system, clamping to a flange. You see that middle picture there. That is a bag that has a piece of material that is meant to sandwich between that metal cage or and that flange there. So that's heavily dependent on is the clamp doing the right amount of work? Is the personnel putting the clamp in the right place? Is it, there's a lot of factors involved there. So that picture to the left is just another design, another way to skin that cat to get you a better seal and better reliability in your equipment. Twist lock. Jerry's going to talk a lot about this. This is MicroPool, Aeropulse specific technology. And this is a kind of a hybrid between a bottom load and a top load. Those of you that are familiar with bag houses. So you are using bottom load technology, bag tuck into cage with clamp, but you're attaching that to a venturi and then feeding it into the top. So you got a lot of moving pieces here. You got a lot of variability and a lot of maintenance involved in getting these things sealed up. Again, just there is another way to go about this, and Jerry will go in more detail on that a little bit later. All right, we talked a little bit earlier about unintended consequences, and this is really just a picture to kind of illustrate some of that. Filters and timer boards and cages are some of the common things that we look at from a preventive maintenance, and hopefully what we work on in a preventive way helps us in that predictive way determine how long those things, those life cycles are going to last. This is one of those unintended consequences where, hey, let's just add a couple more pickup points. What could possibly hurt? We've got some extra fan, or we upgraded the fan. Just know that everything from grain loading and bulk density and all that gets affected by your extra pickup points and dilution air, things like that. So just something else for you guys to consider. While you're looking at bags, cages, please add blowpipes to your cleaning inspections. So blowpipes, this is specific to PulseJet technology. That's not something that you need to check every month or every year, but maybe every change out or every other change out. The holes on the blowpipes need to be round, and they need to be centered over the bag and cage, so that when it goes through a cleaning cycle, you got all that energy going into the bag and not directed somewhere else. So the picture on the left, you're seeing a diagram up top, and then a real world photo of a blowpipe that is slotting. And the middle picture is just got some junk in the blowpipe hole. And the picture to the right is kind of the result of both of those things, or could be. And so this is a picture where you've got high velocity air and dust that is sandblasting through a metal venturi on the top of the cage. And you better believe if it's going to burn through a piece of metal, it's certainly going to burn through some fabric. This next slide is difficult to see, so I'm just going to walk you through kind of what you're looking at here. The picture on the left is just a catwalk. It's just a picture of a catwalk on top of a bag house that guys will walk past through every day. The picture on the right is where the catwalk is actually broken through from its support structure and is laying on top of the bag house. It's not designed to lay on that spot. And the dark section that you see inside that circle is where the insulation has actually cracked, and a hole has begun forming underneath the insulation. It's rotting the bag house out. You're getting leakage, air and water from the top side of the bag house that's now dripping into the bag house, dripping on the bags, killing the bag house. So this is one of those see something, say something moments. If a catwalk is broken, you know it shouldn't be, and you see some cracks in places they shouldn't be, let's say something and get that fixed, because you can never tell where what one little problem can manifest inside the bag house. Jerry's going to spend some additional time on this. Baffle plates, similar to what we just talked about from a gas stream perspective, eating up that venturi. If you have a baffle plate in your bag house, and most pulse jets, most reverse air, most bag houses in general will have a baffle plate. So the diagrams to the right kind of gives you an idea of why you have baffle plates, why they're engineered that way. So you have again, the picture to the left, I'm going to be bouncing back and forth. You only have one spot where air and dust is going to come into a bag house, into a compartment. And the idea is to orient all that and spread it out so that it equally hits all the bags, all the filters at the same time. That's what a baffle plate is there to do. Without it, you're going to have all of that velocity and all that abrasion coming in and just hitting one spot. All right. So the picture that you're looking at here is air and particulate hitting a baffle plate, wearing out a piece of metal. You can see that missing section there. And lo and behold, if it's going to eat through metal, you see the bags there where it's eating right through the media. So add baffle plates to your preventive maintenance. Cages, kind of a fun one. Everybody's, at least in pulse jets, you know, you got some bent cages out there for sure. Preventive maintenance on. But if they're a little bent, sure, bend them back. Picture on the left is a little drastic, and that middle picture even more. Jerry would say it's got scoliosis. But if we got any broken welds or rust, that's a non-starter. Let's not try to reuse those. This slide is all about retrofits, or it's not all about, but it's the first couple pictures there are about retrofit, unintended, again, those unintended consequences. You can kind of see in that top picture, right above the arrow, where the two pieces of metal join. You can see the original section, the original flange that was built with the bag house to stop the pulse pipes, or to add the pulse pipe brackets. So somebody had the great idea when we're changing out the blow pipes to add a flange on there, so we'd have a wider seating area. But you can see the result of that is you can't get that back row of cages out. The cage can't come out. It's gonna hit. You're gonna have to bend the cage to get them out. So when you put them back in, can you guys see this presentation? The middle picture is a spring. I mean, it's technically a spring. It is still there. But is it doing its job? So on a preventive maintenance standpoint, please make sure that you add springs to those guys out there that have reverse airbag houses. And the picture to the right, MagnaHelix, Photohelix gauge. Yeah, technically it's there, but your guess is as good as mine is what it's reading there. So anyway, we're having a little bit of technical issues here, so I hope you guys are running through with us here. All right, the last slide is a little bit, okay, thank you. Last slide is a little bit specific to pleated filters, but it can be applicable to some bottom load bag and cage filters. Clamps, they get reused. Bags and cages, it's very common. And these are stainless steel, and in a lot of cases, it doesn't cause an issue. I only put this in here to illustrate line clamps, why they can be important, why you would use them. Pleated filters, they have a boot that is meant to marry to the bottom hub of a bottom load baghouse system. And I liken these boots to kind of like a banana. The banana peel is really tough. The inside's is kind of squishy and delicate. So the skin on these boots are just the same. As long as we don't cut that skin on the outside of the pleated filter boot, we're in good shape. So we want to limit any sharp objects, any corroded metal that will cut that skin. Because once a cut starts, it will unravel and you'll have problems with these things dropping out. Line clamps is a great way to combat that. With that, I'm going to turn it back over to Jerry, and he's going to go through some case studies.
Thanks, Michael, for that. Again, we'd like to apologize for the technical difficulties. Technology is great when it works, but not so great when it doesn't work. So thank God I'm not in charge of the technology of this presentation, because y'all wouldn't be able to see this from the beginning. So anyway, we apologize. But let's get to the case studies, right? So these case studies I'm going to talk about are things that over the last 6 or so years that I have physically seen with my own eyes, and help assist some of our customers with issues that they have at their particular plants. From climate, from just taking what they're telling me was wrong, going out and climbing through their bag houses, looking at their entire system from pickup points to stack, just trying to figure out what could be causing these issues and coming up with solutions and helping them out. So just wanted to give you guys a few of these things to let you know how we operate and how we've helped people out in the field. Talked about this earlier when I was talking about door seal, correct? Door seal is very, very important. I had a lime plant in Missouri. I'm not going to name the plants that I've been to. I will tell you the industry and the region where I went to, just to kind of, because a lot of that's important, especially when it comes to this particular case study. So I was at a lime plant in Missouri. Lime, Missouri moisture, lime being lime, right? So you can imagine. So they called me up and said, Jerry, we're having premature failures in our bag house. These bags are failing. We don't understand why. So I told him I'm gonna get on a plane. I got on a plane within a few days. I was there. It didn't take me a few days to travel on a plane, because I live a lot closer than that. But anyway, get on a plane, get there, walk up the catwalk. The first thing I see laying on the catwalk, because they're in the middle of a change out, are rusted cages. Immediately I said, they have a moisture issue. So somewhere, somehow, some moisture is getting into their bag house. So I start looking at, the first thing I go to is their door seal. And sure enough, their door seal is messed up. They have a lot of missing door seal. on the bag house. They also, on the doors themselves, the hinges were apart, had come apart, and moisture was coming in. So we talk about negative pressure bag houses earlier, right? When that fan is on the clean side of that, and you live in Missouri where there's, humidity 24/7, it's going to pull that humidity in that bag house. The humidity was climbing up on those bags. That lime was hitting those bags, and it was, as you can imagine, what it was causing those bags to do. Um, this next case study we have, I got a phone call from a steel plant in Oklahoma, and said they were having bags were popping out of their tube sheet on reverse air bag house, as well as they were getting some bypass. So um, I got on a plane, went out there Thanksgiving week. It worked out because my in-laws live in Texas, so I was able to drive down there and eat with them. But anyway, get on site and open up the bag house and start looking, and pulled out my set of calipers, and I mic'd holes in several compartments. And what I found was an inconsistency in the size of the holes as I mic'd those. So what they were using was a 10-ounce fiberglass with membrane with a fiberglass cuff, reverse air bags. What we were able to do, because they were not going to willing to change their tube sheet at the time, because fiberglass doesn't give, we decided to move them. I asked them what their temperature and the temperatures were, and they stayed under 350. So I was able to move them to an aramid cuff, which has a little bit more give to it, so it seal on those inconsistent holes. Um, that fixed that problem. While I was there and miking those holes, I shined my flashlight down into the hopper, and there was dust sitting a foot below that hopper. And that was no good. The hopper was slap full of dust. And if you can think about it, you got a fan that's bringing in so much CFMs, right? That's pulling so much in there. And if that hopper is full of dust, there, it's like a whirlwind in there. And what was happening, it was taking that steel dust and sandblasting the bottom side of that snap band on that tube sheet on those bags. So um, told them about that. They did admit that they had some rotary airlock issues. They have since fixed that. I was there last week, met with those guys, and no bag issues once they changed out those cuffs. Anytime, they changed out those bags with those new cuffs. Anytime they were having bags popping out, they've got rid of their. They started evacuating their hoppers correctly. They've had no issues, and those set of bags have been in there since the end of 2018. So they've lasted them a long time. They're doing a very good job. The next case study, Michael kind of talked about continuous cleaning and cleaning on demand, and what's the difference between the two. I got called out to do some baghouse training, as well as some help them with the installation. I'll talk about that in a few minutes. But I got called out to do some baghouse training at a gypsum plant in Wyoming several years ago. And as I was doing about a 6-hour class on basic baghouse training, I was just telling them the difference between continuous cleaning and cleaning on demand. And as we were doing the baghouse inspections and we was walking around the baghouses looking, we noticed that all of their cleaning systems was set up as continuous cleaning. We also looked at their differential pressure that they had in those baghouses, and it was extremely low. So I told them, I said, you're probably over cleaning your bags. You're probably cleaning too often. And you say, well, what's the problem with that? Well, compressed air costs money. That is a big expense. And the more that you can save on compressed air, the better. And along, I mean, as well, every time you pulse, every time that compressor fires up, and you got to use that pulsing system, you wear out diaphragms. You take the risk of oils or dirt or water getting in your compressed air lines. So the and each bag, the more you pulse it, because that bag flexes and comes back, it does weaken the bag. So 99% of the time, cleaning on demand is the way to go. Continuous cleaning, there it does have a purpose on very, very specific issues, but cleaning on demand. But anyway, so they took this information with Clean on Demand on their own and reached out to the state, and the state gave them a refund on or gave them money towards changing out all of their cleaning systems to be able to clean on demand. So they called me up, told me that information. We quoted them timer boards, photo helix gauges, and all that stuff, and got them, and then pointed them in the right direction, helped them get those things changed out. And I don't know what their end results are as far as cost savings, but I'm sure it's huge. Sorry, guys. We're getting there. All right. This next slide is inlet location. Okay, so I got a call from a carbonate plant in Washington State saying that they were having some premature failures with their baghouse. They were using an aramid with membrane media. It was a micropool twist lock bag house, so top load, and we'll get to that a little bit later in a few minutes because I got another story to tell you about that. Anyway, they were having this aramid was getting holes in them. So first thing they did is they sent me a bag, and me and my technical manager started looking through that bag, and this aramid you can just pull apart with your fingers. It's like it was paper. So that immediately tells me two things. One, it tells me that it was compromised somehow. And it was compromised one or two ways. It was either compromised by heat, but we didn't really see the evidence of that. So we really leaned towards hydrolysis. And aramid does not like moist heat. It doesn't. So I called the company, called the customer and said, hey, look, we believe hydrolysis is going on within this bag house. What is your moisture content? In the first of all, I asked about how the bag house was, where it was located, whatever. And this bag house was actually located inside. So the chances of it really pulling any type of humidity from the outside was it really wasn't that really wasn't the case. So I asked him, so how much moisture, what's the moisture content in your product? And he said it's about 20 to 24%. Ooh, okay. So and there's no way to get rid of that. So we started looking at maybe we need to change the medias, right? Put them into something that's not going to be affected by hydrolysis, whether it was a fiberglass or PTFE. But we knew that PTFE was probably the better fit because there could be some chemical reactions and things like that. So we actually got a purchase order for PTFE bags, and if any of y'all know, PTFE is a very, very expensive product. Compared to aramid, it is quite a bit more. So, but I told him, I said, let's hold up on this order. Let me come on site. Let me wrap my arms around this bag house and see what you really have going on. And we did that. And one of the things that we discovered together was that their inlet was not coming in on the hopper. Their inlet was coming on the side of the bag house. So if you can imagine all this carbonate, which is already abrasive, coming in on the side of that bag house, you have hydrolysis. We know there's heat. We know there's moisture, and now there's abrasion coming in. So talk to the plant engineer. He decided, hey, look, he's gonna propose to his company to move the inlet to the hopper, and then actually put in some diffusers to knock out all that heavy stuff. So before they made the move to go ahead and proceed with the PTFE bags, excuse me, let's change those out. Let's do that first. Excuse me. And they did. So um, once they changed that out, they stuck with the airman bags and no more issues. The bags were given them the life that they wanted out of that. Is the hydrolysis still taking place? Absolutely, it is. But the abrasion is not. And because that ductwork was moved to the bottom, now the entire bags in this bag house are sharing the abrasion, what little there is, and the hydrolysis, not just a hand few of them. Michael talked about this snap band earlier, the slotted snap band. Okay, I mentioned earlier about that gypsum plant in Wyoming. One of the things that I did there is they asked me to help them do a change out. What they had was a MicroPro twist lock bag house. And for any of y'all that know what those are, that is Michael kind of said earlier, it's a top load design that's kind of like a bottom load, right? So I'm going to go through the steps that it takes to change out a bag on a standard MicroPro twist lock. You take a tool, you will untwist the venturi that's sitting on the top of the tube sheet. You'll pull it up. There's a hose clamp in there. There's a worm gear clamp in there. You'll take that. You'll unscrew that and get that loose. You will pop out the venturi, which is locked in there by a bead. You'll pop that out, move that to the side. You'll take the bag. You'll undress it off of the cage, and then you do the exact reverse. You take the cage. You take a bag. You slide a cage in. You fold the bag inside the cage, make sure there's no wrinkles in there. You put the worm gear clamp back on. You pop the venturi in. You take a drill. You tighten up the worm gear clamp. You go up top. You take a gasket, slide it on top of the bag, drop it down into the hole in the tube sheet, twist it in there. You got to use a tool to make sure you torque it correctly and it's twisted in there. All those steps to change out one bag. So we have what we call our slotted snap band, where you can it's actually converts the bag to a standard cage with a built-in venturi, with a regular style DBSR double beaded snap band. So instead of through all those steps, if you were going to change out one of these, you'll pull out that ring, pop out that snap band, or excuse me, you'll pull out your cage, you pull out the ring, pop out pop the snap band, pull the bag out, put a new bag in, snap it in, put the ring in, and drop the cage in. It's probably 20 times faster than it is doing a MicroPro twist lock bag. So we had I have a cement plant in Texas that has some MicroPro twist lock bag houses. And I converted them over to the slotted snap band bag. And I was there on site the first time they put this in, and I thought this old boy that had been there for 30 years was gonna hug me, or I don't know. He was so excited because he dreaded going up and doing these bags because it just took so long, and he saw the benefits, and they're absolutely in love with them and with me. I think this is my last one, right? Okay, so this is my last case study. So, um, same steel plant in Oklahoma. They have a bag house off of one of their burners. And they called me up and they said, "Hey, man, we're getting a lot of holes in these bags." They were already in a high temp bag. They're already in a fiberglass with membrane bag, but they were getting little burn holes in their bags. So I started asking some questions, and I said, well, you know, you've got embers coming in and flying and landing on your bags and causing holes. These are burn holes. Um, I said, you need to stop that. And they said, well, we don't know how to stop that because we really can't control what people throw in this burner. Um, you know, there's all kind of different things. And people say they throw trash in there, pallets in there. I mean, there's all kind of stuff they'll just throw in this burner, and they can't control what's coming in. So we started looking we went, you know, from the pickup point, started just walking through. And then we finally get close to the bag house. And right before the inlet of the bag house, I noticed that there was a box on the ductwork. And I asked the guy, I was like, what's in that box? He said, I don't know. So we climbed up there, and he took the lid off of that box. And what we found out was there was plates inside this box of expanded metal. And that expanded metal was designed to be able to be in there to be able to knock that stuff down. Well, these expanded metals had, like you see in this picture, big gaping holes because they hadn't been changed out in forever. And sure enough, they went and changed those out. Problem went away. Again, I was there last week, visiting with these guys, checking on some stuff, and I asked them how those bags were doing, and they said perfect. But he did mention, he goes, it's probably about time for me to go in and check them plates because over time they are going to wear out. But I think that's all I've got as far as the case studies. I'm going to kind of turn this thing back over to Christy.
Thanks, Jerry. Okay, now it's Q&A time. If you have any questions for us, type them out in the chat box, and we will get to them in the order that we receive them. Jerry, we do have a question, though. Does Menardi offer baghouse inspections?
Absolutely. We spent a lot of time out in the field, climbing through baghouses, looking at people's systems, and for us to understand how their systems work so we know better how to serve them, but also to educate them on how their bags and what their system is doing. So yes, we walk. I say a lot in some of these other questions, or not the questions, but as far as the case studies, we walk from pickup point to stack, um, and help people understand and look at things and write up reports for them so they can, um, you know, change, make their process better.
Okay, thanks, Jerry. Michael, we have one. The attendee wants to know, how does hydrolysis take place?
Yeah, okay. Yeah, appreciate the question. So, fibers used are really broadly categorized into two buckets, if you want to call it that: thermoplastics and condensation polymers. Okay, condensation polymers are going to be your polyesters, your aramids, your P84s. Your thermoplastics will be polypropylene, PPS. So those that are condensation polymers are the way that they're derived, manufactured, is by a process of driving water off during the initial manufacture process. So that's where it derives its strength, is the loss of water. So when you reintroduce water, everything always wants to go back to its original state, its natural state. So that when that water is reintroduced to a condensation polymer, it can weaken those polymer bonds. It can weaken the strength of the media. And polyester has different resistance to hydrolysis as aramid, and those two different resistance as P84. So they each have their own thresholds, and it's a combination of temperature, moisture content, and time. It's all of those things playing together. But there's ways to, a lot of times there's ways to combat that in your process, and or changing from one polymer type to another. So changing from a condensation polymer to a thermoplastic. But it is a at its basis, it is a chemical degradation of the polymer, which results in a loss of strength for the filter bag.
Okay, thanks, Michael. Another question. Can Menardi help supply documentation forms for maintenance to help keep better records of their routines?
We do. We can help you provide that. We have the daily, weekly, monthly, quarterly, annual inspection checklist that Jerry went over earlier in the presentation. So we have copies of that. We have copies of equipment inspection forms, which will help you ID the other things that we talked about, like the tube sheet, the stiffeners on the tube sheet, the duct work, the baffle plates, things like that. And then we have the failed bag charts to help you kind of run down where these problems keep occurring.
Okay, Jerry, we have a new question. What is the optimum cleaning pressure? And how long should we clean the bag?
Well, all right. So the rule of thumb as far as differential pressure, I usually tell people it's 4 to 6. That's a good number that seems to fall in line. But I've seen bags out there, I've seen systems out there where their standard differential pressure is 8 to 10. And their permit allows that, and that's what they go to. Again, I talked about earlier, um, plants that are built 20, 30, 40 years ago were designed to be able to process X amount of product. Now that same plant with the exact same equipment, they're asking it to do 2 or 3 times that. So differential pressures really affect that, and they climb due to that. There are certain things that you can do to get your differential pressure back down to where it needs to be. But as a rule of thumb, your standard differential pressure should be somewhere between 4 and 6.
Okay, I think we've got time for one more question. If our bags are failing, can we send a bag in for it to be analyzed or looked at to determine lifespan or mode of failure?
Yeah, that's some of the things that we can help you with. So we do have a lab here in house at Menardi. It helps us kind of run a post-mortem on a dead bag. It helps fill in some of the gaps. Why things fail? There's lots of different reasons. It can't breathe anymore. It can't. It doesn't have any strength left. So on and so forth. So we have a lab here. We can run. We know what the values are of a brand new filter. Obviously, we know what they are when they're dead. But that time elapsed between start to finish can help you predict how long things are going to last. So we do some spot checks of some bags if needed to help you ID that timeline. So if you don't know what your timeline should be, if you don't have a starting point, bags go in new, give us a bag after a few months, give us a bag after 6 months, whatever it is. We can help you plot that diagram, or I'm sorry, plot that timeline to help you identify a timeline.
I know Christy said that we're running out of time, so I do want to just take just a second and just let everyone know, and I'm sure Christy will probably talk about this, but if you have any more questions as you get off this phone call, this webinar, and you go, oh man, I wish I had asked that, or whatever, whatever something comes to you, please reach out to us, reach out to your Menardi rep, and if they can't answer it, there's someone in our organization that can answer your question, and we can really help you all out.
Thanks, Jerry. And just to piggyback off of that, there is a spot on our website that says contact us, where you can fill out the form and it'll come directly to us, and your rep will get back with you on any answers that you have to your questions. So I'm going to go ahead and we're going to close this up, but I do want to say thank you for joining us. We really appreciate your time. There's also going to be a recorded session that's going to be sent to your email, so you will get a copy of this, and it will be on our website. And before you go, I just ask that you please fill out the survey that you're going to get. It helps us improve our webinars, and we do apologize today for the little technical difficulties that we had. But thank you again, and we do appreciate your time, and we look forward to for you joining us on our next webinar. Take care and keep learning, folks. Thanks.
Thanks, everybody.
Thank you. Hey, we had a